right, thanks, Scott. Yeah, I'm Chris Monaco. As I introduced myself before, I was the CNDH flight software lead on Solar Probe. This talk is about it's entitled "Application Level Solution to Nested Mutual Exclusion Priority Inheritance," and this is very real-timey, very flight software. So I think the flight software developers doing a lot of hands-on stuff might be interested in this. This is a talk where I'm going to describe a problem that we encountered during our Solar Probe flight software development, what we did about it, and our thought processes. And it starts to get a little bit into the weeds. It's a short time slot, so I'm going to show some of those slides, and then I'll be pretty brief towards the end. But I did want to show the slides so they can get captured and people. And they're fairly verbose slides, so you should be able to look at them independently and get a lot of information from them. But essentially, I'm going to be talking about priority inheritance and a nuanced observation about priority inheritance. And I assume most folks know what that means in the context of a real-time system and task scheduling. Yes, a couple, okay, a few. All right, hopefully enough people. And for those who don't, I'm going to describe what that really means. But essentially, it's when a low priority task has a mutex semaphore that a higher priority task is waiting on. So what we believe should happen is that lower priority task its priority should be elevated so that it can get done quickly, release that semaphore and that resource, and let the higher priority task run. And here's just an illustration of that task. P3 is running. It takes a semaphore. It has a semaphore, and for some reason, there's a system clock tick. A high priority task P2 runs, and it wants that semaphore. So task P3 gets elevated to the priority of task P2 until P3 releases that semaphore, and at that moment, its priority gets lowered back down. Once it releases the semaphore under contention, once it releases that, its priority goes back to its native priority. And even if it still wants to run, now it's no longer the highest priority task ready to run, and P2, the operating system will schedule P2 to run, and then when P2 is finally done, or really pens for whatever reason, then P3 can continue to run. That scenario extends to multiple tasks. You can have, task P3 takes a semaphore. It's holding that resource, and as we saw before, task P2 becomes ready for whatever reason. So the OS schedules that to run, and if P2 attempts to take that semaphore, then P3 owns it, so its priority gets elevated, and it will run until it releases that semaphore or gets preempted by a higher priority task. And in this case, P1 is higher priority, and it gets swapped in, and it tries to run. It tries to take that semaphore, and it is yet even higher priority. So once again, P3 gets elevated now to priority P1. It will run until it releases that semaphore. And at this point, the semaphore under contention is released. P1 is the highest priority. It gets to run. And then when it completes, then finally P2 gets to run and take the semaphore. So there's also a scenario where there are two semaphores involved. Let's see. There we go. So in this case, these semaphores are nested, and that nested semaphores should be taken in a stack-like fashion and not, A, B, and then release them in the same order A, B. It should be you take A, take B, release A, like a stack. And this describes that where in this scenario, the inner semaphore of these nested semaphores is the one under contention, and the outer one is really irrelevant, but that is a scenario that I'm going to talk about. So in that case, it's really just this inner semaphore where the priority gets bumped up and then lowered back down when this P3 releases that semaphore. And then later on, there's another semaphore that was taken earlier and released later, but you don't see any priority changes starting earlier and then ending later. It's just around this inner semaphore. But as I understand it, this particular circumstance for a long time for constrained real-time embedded systems, this algorithm, there was no, and this is what I've heard, that there was no practical, implementable solution to this priority inheritance protocol. So the industry standard for a long time for many real-time operating systems was an approximation of that algorithm, which I think has some significant implications when you have nested mutual exclusion semaphores. And this diagram, it starts off the same. It task P3 takes a semaphore, it gets preempted by P2. I skipped a step. Task P3 takes one semaphore, takes a second semaphore, so you have a nested condition. It gets interrupted by P2. P2 wants that inner semaphore, so P3 gets elevated to the priority of P2, but P3 gets to continue to run because it still has that semaphore, and this is part of the resolution of the resource. P3 releases that inner semaphore, and that's the moment when the semaphore under contention is now released. There's no longer contention, but the algorithm of this approximation of the priority inheritance does not release the semaphore right away. I'm sorry, it does not lower the priority back down right away. The trigger in the algorithm to lower the priority back down to its natural default priority is once it has released all semaphores. So you can see here that I'm calling this an extended priority inheritance. So this is a period of time where P3 is running potentially above the priority of other things that, as the lead or the system engineer has determined that they want, it's against that designed priority scheme. So this approximation, there's problems when there are nested mutual exclusion semaphores. Mutual exclusion semaphores are there. They're an important tool to help us protect data or enforce constraints. So an argument could be don't use nested mutual exclusion semaphores. I contend that older real-time systems, or maybe not older is the right word, but there's a certain model of real-time systems where they're, our older flight software systems were highly integrated. It was a single executable application, and there are different tasks and libraries, but at the end of the day, it was a single executable application with different interrelationships and a little bit less software layering. And this is an example from Stereo and Messenger, and those are well over a decade, almost 2 decades old. The lower level operating system, libraries and applications, and that looks like good layering. But our systems now with Core Flight Executive, there's even more layering, and I contend that the more layering you have, the more likely it is that you're going to have nested mutual exclusion semaphores. So now we have on top of the operating system, platform support package, operating system abstraction layer, Core Flight Executive, and then finally your libraries and applications. So there's several additional layers involved now. So what do you do if you're in the situation where your real-time operating system has that priority inheritance approximation? One thing you could do is try to upgrade your operating system, and I think that's probably the best decision in general, but sometimes there are other real-world circumstances that would prevent you from doing this. Other things you can try to do are try to look through, go through your flight software or your software, this is not unique to flight software systems, but try to eliminate nested mutual exclusion semaphores. That may also not be practical because you're reusing a lot of software. And also, if you find yourself in that position, removing semaphores, that's not necessarily straightforward. They're there for a reason, to protect data, resources. So a lot of analysis may need to go into removing semaphores for whatever reason, or in each individual circumstance. Another thing that can help with this problem is to make all critical sections extremely small. I think that's a good idea, but I think in reality, a semaphore is a general tool, and there's no reason why, generally speaking, you can't use a semaphore to protect a low priority resource that is only used by other low priority tasks. So if you start having that involved, if you're using low resources, semaphores to protect low priority, potentially resources that might be needed for a longer period of time, and combine that with resources where you may need to take it and you're holding it for a very brief amount of time that are shared with higher priority tasks, then you start to get into this scenario where you may have an extended, significantly extended priority inheritance condition. And we were seeing that on Solar Probe. We were chasing, and this was during development, we were chasing some issues with our flash file system, and we weren't sure where it was located. And what we did was we put a semaphore around some of the file system operations, which can be long, but those resources were shared by other low priority, long duration tasks where we didn't, if it was held off by a half a second, it's not a big deal. But then if for whatever reason, these file system tasks that are low priority, if they have the semaphore, then they need to send, in our case, it was a CFE software event message. And a CFE software event message takes a mutex, and for a very short period of time. And if it was interrupted during that very short period of time, now we have a nested mutex semaphore scenario. The priority was elevated, and then it was elevated and extended for the amount of time that it held our file system semaphore. So in a real-time system, that's a very problematic condition, and then we would have health monitoring effects, and ultimately it could potentially lead to a reset or not meeting certain deadlines. Let's see. So upgrading our operating system we did consider that. We did look into that. At the time, the latest release version of the operating system we were using had the same implementation. So we could have tried to upgrade to sort of the development head of that operating system, but at the time where we were on Solar Probe, there's definitely, I think, been probably in many cases, the farther you go in a mission, making changes, upgrading your operating system, there's some apprehension around that. So some of the things we thought about is to try to reduce the footprint of the problem, and I mentioned this, eliminate nested mutex semaphores, and I claim that there may potentially be a lot of analysis that's required to do that. Make critical sections as small as possible. That's a great idea in general. We wanted a comprehensive solution. We were also under a schedule constraint. So what we decided to do is collaborate or coordinate with the vendor of the operating system to port in the proper or the textbook priority inheritance protocol into our specific version of the operating system, and we felt that that was a smaller change. Yes, it's a change to our operating system, but we're not upgrading to the latest rev. It shared more of the code base, so we considered doing that, and that was sort of the leading candidate solution at the time. We interacted with the vendor. We started that process. We started going through the contracting, but as we kicked off that process, it looked like it may not be not a short duration process. So I'm not even nearly done with my slides, but I'll getting a 2-minute signal. So then we decided in parallel, let's look at an application level solution. What can we do, if anything? And what we came up with was was or the hypothesis was, can we solve this in the operating system abstraction layer? The operating system abstraction layer, it implements a translation layer to the semaphores. So the problem is kind of enveloped through the operating system abstraction layer. All of our sem takes, all of our sem gives go through the operating system abstraction layer. And 95% of our software, that's an estimate, is above the operating system abstraction layer. So we can sweep up almost all of this issue by, if we can come up with some way to do this in the operating system abstraction layer. There was some analysis to be done for non-OSAL semaphores. Let's see, I am going to have to accelerate this quite a bit, but...
Hi, Chris?
Yes?
We can push the return. Just go ahead and keep going.
Well, we'll meet in the middle. I will accelerate this, and we'll go a few minutes late into lunch. So this solution kind of depended on the fact that the operating system has this approximation of the priority inheritance algorithm. So it works in most cases, but we identify the specific scenarios where we understand that the OS is not lowering the task priority back down. So this solution doesn't have to implement the entire priority inheritance protocol, just that specific case where we need to lower it back down. And essentially in the OSAL, we added bookkeeping and activity around within the OSAL sem takes, sem gives, to track the priority of the task, track the priorities of the tasks who are blocking on the current semaphore that's under contention, and essentially, upon a semaphore release, sem give, then within the OSAL, that specific operation, it detects, is my priority higher than it should be, based on all of the other tasks that are waiting for this particular semaphore. And so there were some assumptions or stipulations that we needed to make in order to get that, I guess, model to work. In that, we were confident that the handling of non-nested semaphores was good. And it's really just that handling of nested semaphores where it doesn't lower the priority back down. If there are semaphores that are not using the OSAL, those need to be considered and handled specifically. There were a couple other constraints or things that we need to make sure that were true, that all tasks that use OSAL semaphores shall be OSAL tasks. That was not true at the beginning of this, and that's actually some feedback to see if the OSAL developers at Goddard. I think that should be enforced. If you're using OSAL semaphores, it should be an OSAL task. And then otherwise, our flight software does not otherwise dynamically change any task priorities. I think that's generally a bad idea for your software to choose dynamically how to adjust the task priorities. This is an exception to that, where in this case, for this particular reason, we want to lower our task priority for that particular task back down to either its native priority or back down to equal the highest priority task of the task waiting on that set of semaphores. So we believed that we could address this within the OSAL. This is where I'm going to, I'm not going to dig in too deep in the weeds. You can look through these slides later, but essentially we did some, within the OSAL sem take, we did some bookkeeping prior to taking the native RTOS semaphore to do tracking of task priorities, and then once we received that semaphore, we did additional bookkeeping, and so a lot of the magic was in that bookkeeping, but really it was when the solution was when you release the semaphore to reevaluate the priority. So I'm going to just show some of these slides and not really start to talk about them, because I did want to move on to something else to wrap up the workshop. And as folks are looking at this, I'm sure that I am not an operating system developer. I'm sure that, that some of my terminology might not be correct. So if you have a PhD in operating systems, or you do that for a living, you might kind of chuckle at some of the terminology. But yeah, these slides just get pretty deep into the weeds. So I think I've communicated what I'd like to. And I wanted to say a few words about wrapping up the workshop. Okay.
You want to take a question or two?
Oh, yeah, we'll do that. Are there any? I know I skipped over a lot of detail towards the end there, but in terms of the concept or comments, any questions?
Questions? How did you verify this?
We did a lot of targeted testing. I mean, it's the kind of things that you would, when you can construct a lot of these scenarios around priority inheritance. We did a lot of that concocted testing where, it was within our system, but we would add some test software. So we would, have some additional tasks, taking semaphores. We're looking at the priorities, and we tried to come up with a lot of different scenarios and show that, before and after, before we use this and after we add it in there, and we map, as many of the scenarios as we could come up with that show that the algorithm works. We did a lot of reviews around this code. We had folks at NASA Goddard come in, a lot of the OSAL developers come in and give us feedback on the algorithm and the code reviews. We also had enough evidence and logging around the within the flight software where we were able to detect when these conditions were happening. And then after introducing this, we were able to show that in those conditions where we were seeing this, it's no longer happening. So I mean, we did a lot of targeted testing, and we were able to run through our stress testing and system testing, and with the tools and the logging that we had in there, we were able to show that within those more demanding stress scenarios that we were no longer seeing these conditions. So yeah, is that good? Okay.
All right, one more, please.
Go ahead.
So first question is, did you notice any overhead impact, and
Yes,
did you measure
we did.
it?
Absolutely. So Solar Probe had it was a very challenging mission. The software had a lot to do. The single board computer was relatively constrained. So we, for throughout the mission, we had our eyes looking at CPU loading and trying to make sure that it didn't get too high. So an interesting anecdote, we leveraged a lot of flight software from Van Allen probes, but then going through Solar Probes, that single board computer, it was in some regard, it was less efficient than we had anticipated. So that is what initially kicked off this mindset of making sure that we have our eyes on CPU loading. And we had to go through a lot of the heritage software from Van Allen and make it more efficient. And then when we did this was a scenario where we have a problem, we need to come up with a solution. We kick off the vendor to start working on updating or porting in the latest, the textbook priority inheritance protocol. Meanwhile, we're seeing if we can do something and make sure our schedule doesn't slip. So we come up with this, and it did add actually 4% loading on top of the baseline in the more stressful scenarios. And so that was actually almost intolerable to add that additional 4%. And sort of, on the heels of this, it kicked off another iteration of let's look at our CPU loading, let's look for anything that's inefficient. We may have to refactor, certain things, and then throughout that effort, we actually were able to reclaim 4%. So those two things, combined, it turned out to be a net zero increase in the CPU loading. But absolutely, it was an overhead hit. So I think this is just an interesting example of, the kinds of problems that you might see, and I think it's also an interesting example of how you can leverage something like the OSAL in a creative way to solve a problem.
Next question is, are you planning on open sourcing the solution?
I'm not sure about open sourcing necessarily, but I mean, this was funded under a NASA mission, so I know that there's ways to get it. I'm not as familiar with the nuts and bolts on how to do that, but I think that there are ways to do that, and perhaps making it open source would be good, but yeah. So,
Thanks, Chris.
Any other questions? Okay. I wanted to just say a few words about the workshop and wrapping up. So the presentation